This problem is a two-dimensional kinematic problem. So that means we need to use kinematic equations twice, one for the x direction, one for the y direction. We are given the following. So we have the height of the cliff. So that's when the car is first about to jump off. It's going to be y naught is 10.0 meters. We have the bottom of the cliff, which the car will end up eventually. So that's y final equals to 0. And we have the initial velocity of the car in the x direction. So that's going to be, I'm actually going to say v naught x as the proper notation. So that's going to equal to 20.0 meters per second. Okay. From there, we can actually come up with a lot of other knowns. So these are the knowns that are explicitly given to us, but we can come up with a lot of other knowns. For example, when the car first jumps off the cliff, that's when I want to start the problem. So I'm going to say that x naught is going to be 0 at the very edge of the cliff before the stunt driver gets off of it. We can say that, since there's no acceleration in the x direction, so acceleration in the x direction is 0, then the final velocity in the x direction is going to also be 20.0 meters per second. I could also say that the acceleration in the y direction is going to be negative g, which is negative 9.8 meters per second squared. Now, this is something that, we should just know because, well, the stunt driver and the stunt is going to be on the surface of the earth. So acceleration in the y direction is always going to be negative g no matter what. And what we want to find is the final x placement when the driver is on the ground. So I'm going to go ahead and just go straight off and try to get an equation that has this and as much as the knowns as possible. The best equation out of the 4 options for kinematic equations that we have is x final is x initial plus v naught delta t plus 1/2 a delta t squared. So this is the best equation we have. That's we have the other 3, but they won't have as many of the knowns, and some of them won't even have the unknowns. So this is clearly the best. X naught is actually going to be 0, and let's try to get all this in the x direction. So the x component in the a and the x component in the v naught. The x component's acceleration is also going to be 0. So that means everything that's associated with that term is 0, or at least reduces to 0 when multiplied by that 0. So x final is going to be x, or v naught x times delta t. Becomes a lot easier now. This is what we need to find. This is what we know. And this is what we don't know. Shoot. So we don't know 2 things, and that's going to be a problem because equations only solve for one unknown. So that's the problem. This is why we need to go on to a side quest. All caps. Okay, so the side quest basically means we need to find delta t through some other means before we can go back to this original problem. Okay, so this was all in the x component. That's the problem. We only use the x component, which is great, but we're forgetting that there's a y component as well. Now, generally speaking, if you want to combine or you want to use information of how an object moves in the y component into an equation that is associated with the x component motion, if you ever want to connect those 2 dimensions together, time is virtually the only way that we do it in these kinds of problems. So we need to find time, since time is a universal parameter for these 2 dimensions here. Okay, so how do you find the time? Well, in this case, we need to find the time for the car to simply fall from the edge of the cliff. So we don't care that the car is going to do an arc. All we care about is that since both components of movement are independent from each other, we just care how long does it take for a car to just free fall from the top of the cliff, because that's going to be the same amount of time it takes the car to go in that parabolic shape. So we do that by using another equation. YF this time is equal to y naught plus v naught y delta time plus 1/2 ay delta time squared. And notice that delta time does not have a y or x subscript because it's universal. The initial velocity in the y direction, we didn't write this down, but it is known. The initial velocity in the y direction is 0 as well. So I'm just going to have that as a little separate thing. The initial position is known. The acceleration in the y direction is known, and delta time is what we need to find. So I'm going to square it. And then the final y position is also known, as we've going to define it as 0. So now we're going to go ahead and isolate t. Okay, delta t is then going to equal to negative y naught times 2 divided by a square rooted. So kind of a hefty equation, but when we plug it in, it all becomes simpler. Y naught is 10, a is negative 9.8. Plugging that all in, we get that delta t is 1.42857 seconds. Now I'm just going to keep as many sig figs as possible because we'll reduce the amount of sig figs at the end to a reasonable amount. Okay, side quest is over. Now let's go back to our original problem. We have x final is equal to v naught x times delta t. We know what v naught x is now. We know what delta t is. We want to find x final. Good to go. V naught x is 20 and delta t is 1.42857. Therefore, x final is going to be 28.57 and a few other decimal places, but we're just going to reduce it down to 4 sig figs, and that is the final answer. So in recap, we had to list both dimensions and use proper subscripts for that of this particular situation. We write down the kinematic equation that most directly affects to find the final product that we want to achieve, right? So we use the kinematic equation that has the final thing that we want to find. We see that, most likely there's going to be more than one unknown. So we do a side quest to figure out the other unknown. Generally, the side quest means we have to use the other dimensions of this problem, which in this case is the y dimension, and find some universal factor that can be plugged in here, finally giving you the answer.